Hello, good morning. Yes, been a very busy week for me. I've been out like nearly every night. Yeah, for some gatherings. It's closing to the Chinese New Year, and we just basically like Christmas. We just gather every night. Try to. I'm so full every night, and I feel like I kind of need to explore for having all the food. Yes. Thank you for reminding me to do all this video. I'll try my best to video most of the content this morning. So I'll have like clip 4, clip 5, hopefully clip 6 ready for you. Then yeah, after that there will be no more video class. I'll be back. Yeah, you'll be fine. Let's try to go through the next level. Not next level, basically the next ideas. We've been doing thermochemical dynamics. There's one topic I really doubt that they should put that back into year 11, but they have to move. They just move to a year 12 course, which is about gas law. So in gas law, I do remember I have done a little bit last year about gas law. When we look at gas law, it's very simple that we know we look at one thing just called gases molecules or gas particles in particular. Particles, molecules, in this area we don't really need to worry too much. Just why do we all normally say like gases, particles? Because it's been a important theory that's proposed. We've learned this theory called particle theories for a long time. So if you learn science in year 7, then particle theory would not be too strange, or you will be familiar with it because most of the science teacher would draw you this particular pictures saying that if we have all the particles are stuck together and they're very tightly bonded with each other and they're very close and they're fully packed, we call them solid. So this is what particle theories come from, because we can't punch through it. It's solid. It's very solid, and there's all particles fully packed with one another. Then if you increase the temperature, you start melting. If you melt it, so what do we have? We basically, in a given space, we have kind of less. or you can imagine the whole thing melt, become liquid. And in terms of liquid, we have a bit more irregular shape, and all of the particle will spread a bit more further from each other, but somehow they generally still connect to one another with another force. So then after that, we will have evaporating. So when things evaporate, you turn liquid form into gas. And in terms of gas particle, basically you have all the particles around from basically move further from each other. We just describe this situation saying that all the molecule or particles are not really related to one another. They not restricted by each other. So what do I say? What restricted by each other? If you move anything in the solid, one particle, it will, because they're so packed, you move one, you have to move the other one. While when you look at liquid, in liquid water, let's say, if you burn one thing, you still do the other. If you try to move one, you're likely to move another, because they do have some linkage. We call them like those intermolecular force. They still have the force attaching one another. When you move one, you always influence the others. When you say evaporations or atomization or evaporations, all these terms, they just focus on one concept, and those concept is the particles are so far apart from each other. Even you try to move one, the other would not get affected. So let's say I cross this one out and I'll move this on this side. If I move this particular particle from one to the other side, that's still there. It doesn't really, all the others still basically behave exactly the same, is independently behave and not affecting one another. And this is what gaseous particle, gaseous molecules are so special or kind of like unique from the solid and the liquid. And this generally we call this particle theory. And this particle theory apply the most in the gaseous particle. And gas law based on this particle and the theory I just mentioned behind, they independently behave, not affecting one another. So what happens if you have when you try to look at gaseous particle will have three factors. What are they? The very first one, all gaseous particle would have a given volume, right? How do we measure any gases? We put a container, yes, or even a balloon. So you trap those gas particles inside. It make a volume. So you have 10 liters compared with 2 liters. You will have a bigger balloon compared with a smaller balloon. The second thing is pressure. As gaseous particles are moving around each other, because they move, they will apply the force on the wall of the container. If all the gaseous particles kind of like hitting 1 and 2 and 3 and 4, and that particular not pattern, the frequencies, that frequency would kind of apply the pressure on the wall. If you basically increase the pattern, increase the heat, so get faster, and we call them higher pressure. So pressure, when is another important terms for us to. Oh, sorry, I've got things not really working. The pens. Yep, back. So the second factor is pressure, and it's been a long time people measuring pressure. So there's all around the world they have different what they call unit to measure them. The one that you use the most would be called kilopascal, kPa, and there's all around the world using different things. There's some strange term called millimeters Hg, mmHg. Hg stands for mercury, and there's a particular device that uses mercury to measure air pressure, and we use that as one of the units in the old days. People use bars, and people use something called atmosphere. So atmosphere means the normal, like in sea levels, when you be at sea level, all the gases above you exert the pressure on your shoulder, and that's the atmosphere pressure, or 1 atmosphere pressure. When you move up, you have less and less air above you, then the pressure will go down, will drop a bit. So that the second factors and those units that you use. The last one that we focus on when you look at gaseous particle would be temperature. Hot air balloon. So if I say hot air balloon, you should be kind of ring the bell, knowing that the higher the temperature, the less the density, because the hot air balloon kind of like rise when you heat up the air. Those factors would be important, and also would be the parameters that we use to develop the formula or develop the gases law. The most important one that you do need to remember, we call them gas equations. I'll break the gases equation down into 3 little one later on, but this is one of the major ones that most of the students remember, and it's easy to do it. P, pressure, times by volume equals to nRT. So all of them it is in your data booklet, and it's not hard to remember. PV equals to nRT. And the hardest thing to remember is not the equations, it's the unit that you use for each one. The pressure that you use is kilopascal. The volume, the unit that you use is the liters. And the N stands for number of mole, so we have mole as the unit. R is a what we call them constant, and this constant is particular values is equals to 8.31, and the unit is not that important for this. But the most, and not the most, but the last one that we use is temperature. You may think our temperature easy would be degrees Celsius. No, we never use degrees Celsius in gases equation because we always like to use absolute zero to add as a starting point, and 0 degree is just a freezing point of water. It's not absolute. It's not good enough. Then we always use another scale we call Kelvin, and Kelvin is similar to degrees Celsius in the sense of the energy, like the from 1 into 2 is exactly the same. So while when you try to look at Fahrenheit, 1 Fahrenheit would be smaller than degrees Celsius, but 1 Kelvin is equals to 1 degrees. Basically, the way the scale, the change is the same, while the differences is the starting point. The starting point of Kelvin is never negative. It's always positive. It starts from 0 and then all the way up to like millions of millions of millions. It's just getting higher and higher. But degrees Celsius, for 0, you can get below 0 degrees Celsius. So that can be negative, and Kelvin cannot be negative. And it's the good thing about scientists. They always say, why bother doing negative? And we have positive to deal with if we just set this up as an absolute 0. Then for gases equation, you can see that there are more than 3 factors. You have pressure as kPa, volume as liters. You have temperature as Kelvin. There's one more thing that you will see is mole. And this is basically not hard to imagine, because if I give you 1 mole of gas compared with 2 mole of gas, there would be difference, yes? And that's very important when you look at any gases or any chemical reactions. The amount of the particles that you use, or the amount of the materials that you use, is quite important. So like 1, 2, 3, 4 factors. Then as I say, I will try to break this gas equation down into 3 smaller ones. The 3 smaller ones, based on very easy practice. Imagine if you have a balloon, right? If you have a balloon, then if you increase the volume, yes, increase the volume, what happened to the pressure? Right? If you increase the volume, then let's say you don't have anything in, you didn't put any more gases in, exactly the same, compare with a bigger balloon inside. Let's say, just imagine you only have like a little bit gaseous particle in there, right? If you just increase the volume, you don't change anything, you keep the temperature the same, and you basically keep the amount exactly the same. So we have the same temperature and number of mole. Right, the same temperature and mole. If you increase the volume from 1 into 2, so I just write down the same number of particles on there. And what happened to those particles? The particle will just spread around. And if the first diagram there saying about the frequencies of the gaseous particle hitting the wall of the balloon is like 10 times per second. Then because the second one there, if you increase the volume, it's less likely for each of the molecules hit the wall because there's more rooms in there and it's harder to hit the balloon. Then you realize the pressure in there would decrease. Right? So, but this one, we need to know one thing is if you let's say if you put 1 mole in here and 1 mole in there, we need to be at the same temperature. Let's say the room temperatures applied on both sides. At room temperature, if you put 1 mole in the first one and 1 mole in the second one, both of them has 2 different volume. The bigger volume will have less pressure. Right? The other easy example to think of is a syringe. So if you have a syringe, you have all the gaseous particle there. Let's say we seal this one and doesn't let any gas to come out, or you just simply use your thumb to press against the end of it. What do you think is, what if we apply the pressure and push the plunge in? So this is the first one. After that, you push it in. So you have the same syringe, but that one push it in much further. And you have all the gaseous particles push against each other. This is number 2. So when you apply the force into there, and you say we have exactly the same number of mole and exactly the same temperature. And what will happen is, from 1 to 2, you decrease the volume, but increase the pressure. Right? It's getting harder and harder for you to push it in. Then, by looking at those 2 examples, you realize if you increase the volume, you decrease the pressure. If you decrease the pressure, you decrease the volume, you increase the pressure. They are inversely proportional to each other. Yes? How do we show as a mathematicals to say the 2 situations? 1, we know that is 1 pressure times by 1 volume. And then the 2 pressure times by 2 volume. As there's nothing changed in terms of the amount in there, the pressure times by volume would equal at the first situation would be the same as the second situation. And it makes sense if the first one has 1 atm with 1 liter and is 1 times by 1. Then if you just push it, let's say halfway through, then you imagine the volume get decreased from 1 liters into 0.5, and your pressure will get doubles. So from 1 into 2 atm, and you can see the pressure is 2 times by 0.5. Both of them will be exactly the same with one another. If you're looking at this formula, this is the one tiny one, 1/3 that kind of contribute to the gas equations. P and V, they are next to each other. When they're next to each other, it means that they are inversely proportional from each other. When one increase, the other would drop. Right? So P and V put next to each other. Then you develop 1/3 of the gas equations. As I say, there's three main factors. The three main factors: pressure. We deal with pressure and volume. And what do we do next? We try to deal with the pressure and the temperature. Pressure and the temperature is extremely easy to explain. Let's say you have a sealed compartment. Let's say this is a steel container. You try to put some gases in there. At 20 degrees, nothing happens, yes? You just need to put it under the flame. And you heat this up. And after that, you increase the whole thing so hot, turn that into red hot. And your temperature is no longer at 20 degrees. It's at 2000 degrees. What do you think would happen inside the container? The particle will run crazy. You have exactly the same amount there. You didn't add into it. But because they went crazy, they're more likely to hit against the wall. It's a steel container, so you can't really release the pressure. You can imagine the pressure would definitely go extremely high, because from 20 degrees to 2000 degrees is more like 100 times difference. And the gaseous particle and the gaseous pressure there would increase a lot, from maybe from 1 to 100. That's slightly less than 100. So if we understand, they are basically, when you increase the pressure, increase the temperature, so you increase the pressure as well. The formula would be easy to write, because P1 over T1 equals to P2 over T2. If things that are inverse proportional from each other, we put them next to each other, use multiplications. When the things that increase and increase, we call them proportional, directly proportional with one another. Then we put them as a fractions. P1, T1. Let's make it into numbers. So we at 20 degrees. At 20 degrees, it's funny to say that, as I say, we have to change that into Kelvin. How do we change everything into Kelvin? We need to understand a concept called absolute zero. If you watch TV or whatever games, that you always talk about this absolute zero. Absolute zero means that it's the lowest temperature ever. You would never go beyond absolute zero. So if a certain thing that go beyond, it means that it's not absolute zero. So absolute zero means one thing, is about the concept that we just discussed. If there's a 20 degrees, the gap between the gaseous particle would be less compared with the gap between the one that with 2000 degrees. So if you look at the situations, that is 20 degrees. That would be 100 degrees. If you go bigger, you suppose the gaseous particle would be further from each other if the volume is, if you didn't trap them. What if you go backwards from 20 degrees into 0 degrees? From 0 degrees into negative 100 degrees, you expect the gaseous particle would be kind of like coming closer and closer and closer to each other. And according to this theory, if you try to go further and further and further, you will reach a point that everything will start with one another. And there's no gap at all. When there's no gap, that equals to absolute zero. Absolute zero is the gaseous particles, the smallest gas particle, when they come together so close, that's like a solid, or even beyond solid. Solids still have gaps. They're so close and so close to each other, then becomes no more gaps. And we count absolute zero, we call them 0K. And what would be the values in terms of degrees Celsius? And 0K is equals to negative 273K. Maybe I have a point something, I can't remember that. But 273 is the one that we need to use in year 12. Now, what is 20 degrees? 20 degrees, if you measure by Kelvin, is because 0 degrees Celsius would be 273 Kelvin, as like 0K equals to negative 273 degrees Celsius. Then, if it's 20 degrees, all you need to do is using 20 plus 273, it's 293 Kelvin. Let's say the pressure, the pressure there would be 1 initially. So 1 pressure ATM with 293 K. And what happened to the pressure, the new pressure, when you increase the temperature into 2000 degrees Celsius? 2000 degrees Celsius plus 273 would give you 2273 Kelvin. So it's 2273 Kelvin. From 293 to 2002, the 2027, let's try to do this. 2273 divided by 273. How many times it get increased? It's 8.32. Come on. 8.83. 8.83 atmosphere. Right, instead of saying that I predict it wrong completely, it's not 100 times difference at all. Even though the 20 degrees into 2000 degrees looks like it's like 100 times difference. But eventually, if you look at the Kelvin, the kind of scale, there's only 8.83 difference from each other. And the new pressure there would be 8.83. Right? Makes sense? So that is the second part of the equations. If you look at the equations, you'll see the T is on the opposite side from the after the equals, because when you move this across, the T back down there, you'll find that it would be, is it a bit darker? It's funny. Yes, the T is on this side, so if you move this across, it would be like a fraction, as the lower side of the fraction number. So very quickly, let's go through the last one today. When you try to look at pressure and temperature, and we've done the pressure and the volume, and the only thing that we want to do is the volume with the temperature. So if you try to against those two, that means we try to keep the number of mole and the pressure the same. If we've got that the same, I can't even read my writing, but you can do it. Volume and temperature. So at the same pressure, that one you can imagine go back to look at the syringe again, but this time the plunge of that is able to move, so that one is flexible. When it's flexible, you can move up and down. Let's say we seal this one. Right? Then you put this one there in a freezer. Let's say we put that in a freezer as a negative 20 degrees. Exactly the same one. Let's try to copy this. I like to do this. Exactly the same one. Exactly the same one, but this time I put it in a very, like, in case that's a glass one, it won't melt. 500 degrees. Right? 500 degrees. So for lower temperature and higher temperature, you can imagine what happens when you have this, what happened to this syringe. And this syringe, instead of doing exactly the same volume, you push that way. The gas is inside because it moves so quickly, it expands. So easy. Temperature, expand. Hot air rises or hot air expand. That's basically we learned it from many years ago. Then, but the thing is, we would like to do calculations. What would be, we need to find out the volume if would get increased if you increase the temperature. So if they are directly proportional from each other, so we can try to say V over T, 1 and 1 equals to V2 over T2. Yes? So volume, let's say the syringe there, initially we have 10 ml. And what would be the final volume if we try to increase that from negative 20 degrees into 500? The volume is 10 ml. Then the initial temperature is negative 20. But negative 20 is not exactly what we want. We need to change it in Kelvin. Negative 20 plus 273 Kelvin would give you 253 K. As 0 means negative 20, negative 73 K. Then 253 is what we want. Then the second volume is what we would like to find out, and the temperature is 500 degrees Celsius. You need to plus 273, always plus 273. You never take away. No matter you have a negative degree Celsius or what, always plus 273. That one is 773. So if we have 773 K, then from 253 to 773, 773 divided by 253, how many times? It would be 3.05 times more. 2.05, 3.05, that means the volume would be 3.05 times, so 10 times 3.05 times bigger, which is 30.5 ml. So if you talk about this is 10 ml, then the syringe would be like moving up right here into 30 ml. Roughly. Get expanded 3 times. Even the temperature seems like negative 20 degrees to 500, but the volume would not change huge, like 10 times, 20 times. It would be about 3 times bigger. Right? So we have discussed 3 little equations. That's the third one. That is the second one. And that is the first one. If you imagine all three together, get back down into, let's say, go that together. P1 V1 equals to P2 V2, P1 T1 equals to P2 T2, and V1 T1 equals to V2 T2. Something in common, something that is P and V are next to each other. P and T are opposite. V and T are opposite. If we join those together, you will develop a thing called combined gas law. P1 V1 over T1 equals to P2 V2 over T2. Right? Yeah, it's been quite it's 35 minutes. So that's kind of the maximum times for each videos. Like, yeah, I'd like you to go through some of the gas law questions from now, and I'll give you some, it's time to do some guided questions. So it's question time. Then try to go through some of the questions yourself. Then basically apply those concepts. The most important thing that you need to do is to make sure that you know all different units of them. Right? And next class, I will try to give you a detailed explanation for combined gas law as well as the pressure unit. That's the pressure most of the time is the hardest one to remember, and I hope that I will able to help you out a bit. Okay, yes, done. Try to start doing some questions. Thank you.